Good afternoon, everybody. Thank you for being here. Today, we have the pleasure of having Professor Dana Anderson. Professor Dana Anderson is a big name in cold atom physics, and he's the Chief Technology Officer and founder of the startup ColdQuanta. And in addition, he's a professor at the University of Colorado, the fellow of the JILA Institute there, and professor of the Department of Physics and the Electrical Department, Computer and Energy Engineering, so many things. He's a fellow of the American Physical Society and recipient of numerous honors, most recently the Willis E Award for pioneering contributions to the field of atomtronics. So it's really a pleasure to have him here. And also I should thank the guys that are here now. So we have a paddle tournament that the bus is leaving after the seminar. So thank you guys for being here, even with the paddle tournament. So Professor Anderson, it's really a pleasure to have you here. Thank you so much for your time and for your kindness. And I know that it's very early for you. So it's really a pleasure and an honor for us to hear your talk. Thank you so much. You can go ahead.
It's a pleasure to be online with you. I'd rather be there, but we'll look to have that happen at some future time. And as we, can you hear me okay?
Yes, we can hear you. I was just saying that you're warmly welcome to visit us physically too, anytime.
That's the plan, I hope. And I do prefer, if you have questions, don't hesitate to interrupt me. Understand that there may be a delay, so you might have to be forceful so that I can know you're trying to talk. So this presentation is meant to be a combination of some physics and some worldviews about quantum technology, and it's titled Quantum in the Kitchen, because I believe that, well, that seems more or less far-fetched, that eventually quantum will be so everyday, so familiar, that it'll be sitting next to your sink or toaster in the home. So, you know, there's been a lot of hubbub, a lot of hype surrounding quantum technology. Here's a report that came out. It's actually quite old by now. It came out 2 years ago, more or less, that says that the computing market alone will reach 21 billion by 2025. I'm sorry, actually, this is about all of quantum technology. So what's all the fuss? Well, from a physicist, I thought I'd give you this point of view. You know, one can ask when there's a lot of hype, is it fashion or is it real? And here, I think quantum is here to stay and to change the world. And it's because the laws of physics dictate the limits of how well any task whatsoever can be performed. And that's true whether the task is information processing, sensing, what have you, given a finite set of resources. Physics tells you how well you can make a measurement, how well you can process the information. And today, are we okay on the view? Okay. Today, modern technology has brought us to the point in which the quantum limit, as we would call it, is accessible to an increasingly broader range of applications. So for the future, if you're not operating at the quantum limit, you will not be competitive. And this can be true whether you're designing that your business is automobiles or finances, maybe high-speed trade, stock trading, for example. Eventually, we would like to see all things operating in the quantum limit. And if you're not, you won't be competitive with others that are. And so I believe that quantum technology is bringing about a technology revolution. So for many of us, at least over here in the US, I've noticed tremendously, and in Europe, for example, I haven't been there yet, but you can tell me, the word quantum is mentally followed by the word computing for many lay people. And we know there's a lot of excitement over quantum computing with IBM putting its machines on the cloud, with IonQ doing ion-based quantum computing, and Xanadu does optically photonic-based quantum computing. But in fact, many of us has been in a different kind of quantum business for a very long time. And so the way to think about things is computing is simply the tip of the iceberg of quantum technology, the tip that many people see, but underneath the surface of the water are things like timekeeping, positioning, navigation, signal processing, communications, quantum networks, quantum sensing, and on, whether you're in financial trading or biology or chemistry or earth monitoring, quantum has a role to play. And so let me scale you by looking at humankind's most quantum thing today. So think of it as telling what's coming. So here are two relatively recent papers. They were published in 2019, about 3 years ago already. Seems like time is flying by. Both papers by folks not too far from me where I'm sitting, one at NIST, one at my own institute, JILA. And what you see on the right here is a measurement of clock performance. So this is how long you average the clock signal for. This is its uncertainty, and down is good. And right here up in this corner is the system, the cesium clock that keeps world time in the US, in Europe, and the UK, in Japan, just about every country that has a precision measurement outfit that tells the time for that country uses this cesium clock. And today, the quantum clock is about 1 million times better than the world timekeepers. 1 million times better. That's not just a little bit, that's huge. And here is a more recent paper. This came out in published in February 2022. And this is truly remarkable in my mind. This is atoms over here on the right. We'll talk more about this, but over here on the right is a resonator, optical resonator, and the interference pattern due to light holding up strontium atoms against gravity, and they're being interrogated. And the uncertainty of the time of these strontium atoms is less than a part in 10 to the 20th. And it is so precise that the atoms here tick differently than the atoms just 3 millimeters higher. 3 millimeters higher, they tick differently because they're in a different gravitational potential. That's unbelievable. All right, is there a question?
No, there's no question, Professor.
Okay, so this is to tell us what's to come out of quantum technology, is this factor of, if not 1 million, maybe 100 or something like that, where we trade off performance for cost or something. But 1 million is just an incredible factor. Another example, and this example was all the way back in 1980, where they used Rydberg states of atoms. Rydberg states are just the states of an atom where the one electron is very, very highly excited. And they used a Rydberg atom to detect 100 gigahertz microwave radiation. So just to scale you, your cell phone operates at about 2.4 gigahertz, microwave oven. This is 100 gigahertz.
Professor,
January 9th, yep.
just we are having a little technical issue with the camera. Maybe our camera may be disconnected for a second, but we continue to see you and to hear you. If it gets disconnected, don't worry, we'll be back in a second.
Okay, so okay, I will continue.
Continue.
The performance of a detector is measured in terms of noise equivalent power, and here it was about 1/10 of an attowatt per root hertz. Now, you may not know what significance that is, but just to compare, from 2010 there was a paper talking about space terahertz technology. So that's 30 years later, where they're reporting 3 times 10 to the minus 17 watts per root hertz, so about 10 attawatts at about the same frequency, 97 gigahertz. All right. So 30 years ago, there was a factor of 100 in, 30 years before the superconductor performance was a factor of 100 performance out of cold Rydberg atoms. But in those days, the technology of Rydberg atoms was not so advanced to make easy use of them. And in fact, it was quite expensive in those days to do those demonstrations. So the so what factor, as I call it, why are we doing this? What's it good for? The so what factor is that quantum technology has potential of providing solutions that are a factor of 100 to 1,000,000 times better than much of what we have today in many technological arenas. And in many cases, it provides capability not possible with classical systems, such as what a quantum computer does, or quantum network, or quantum secure communications. So the way I think about it is in the late 1940s, due to the invention of transistor, that brought us the digital age, or digital wave, if you like, of technology. About 10 years later or so was the invention of the laser. And that tide made us a global community by tying together the world with fiber optics in conjunction also with satellite communications systems and so on. And I think that we're on a quantum age. And my own bit bias, but I think you'll see why, is that it's brought about by having exquisite control over the atoms. And you'll see later various kinds of atomic instrumentation that can be applied for secure communications, for new sensing systems, for example, RF sensing, quantum positioning systems, as we like to call them, computing, and so on. So I'm going to be talking about quantum technology based on atoms. And to begin with, where is all the capability come from? Well, it comes from something I expect you're familiar with, which is that atoms are extraordinarily color selective. So atoms will respond to a very specific frequency of light or color of light. And not much happens when you shine on the wrong frequency, but a lot happens, namely they absorb the light and then re-emit it when you strike the atom with resonant light. And of course, as you may also well know, different kinds of atoms have different resonant frequency, and even a single atom has several different resonant frequencies it will respond strongly to. So the utility of atoms comes about very much because they're very, very picky. So let me give you some calibration. We use a lot rubidium atoms. They're in the first column, left-hand column of the periodic table. Rubidium is very easy to work with. It's inexpensive. You can control it with low-power laser diode technology. And we think of it as the silicon of sensors, information processing, and so on. So again, to scale you, here's a rubidium atom. And its resonant frequency is 3.8423109, a little less than this, around this, times 10 to the 4 hertz. So that's 1, 2, 3, 4, 5, 6, 7, 8 significant digits I've written down the frequency on. And I'm going to tune the laser by just these last 2 digits. And at these last 2 digits, I can change the atom controlling the frequency of the laser beam from being weakly responding to very strongly responding. Okay, so that tells you something about the selectivity, the fact that it's these last 8 or so significant figures, and then I change the last significant figure and the atom knows about it. By comparison, let me tell you about strontium. Strontium is incredibly frequency selective. It is used for the world's most accurate clocks. So is ytterbium, but I'm going to do strontium. And here's how many digits I've written down for strontium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The 17th and 18th digit I'm going to adjust of the laser frequency times 10 to the 14 hertz here. And these last two digits, weakly responding, and finally when I get it directly on resonance. But the fact that there are so many significant figures of sensitivity of the strontium to laser light makes it, that's why it's such a good clock, and it turns out it's good for a lot of other things. In fact, there are lots of useful atoms: cesium, potassium, ytterbium, mercury, barium, all for different reasons for the special characteristics for the job at hand. Now I'm going to tell you about some of the tools we use and the remarkable phenomena, starting with laser cooling. You know, I can see most of you who are sitting there, so who knows about laser cooling? Could you raise your hand? Oh, good. So good handful, but not everybody. Well, don't worry. This is pretty introductory. So if I have an atom here, here's this green thing is an atom, and I shine a laser beam on resonance, it could absorb that atom, receive a kick, absorb the photon and receive a kick. And if I shine more photons, brighter beam, it will receive a bigger kick. Now, laser cooling was developed in the 1980s, and these three physicists received the Nobel Prize. Steve Chu, he used to be the Secretary of State, Secretary of Energy after his Nobel Prize for the US, Claude Cohen-Tenuji in France, Bill Philip at NIST in Maryland. And the idea is this: you take a laser that's tuned to the red side, that is below its resonant frequency, and we already did laser cooking. Now we're going to do laser cooling. I'm going to shine two laser beams, one from the left and one to the right, but they're tuned to the low side of resonance. So an atom sitting there would not see the light very strongly at all. So here I'm going to place an atom, and suppose it's moving to the left. Well, as it moves to the left, it sees a higher frequency that's Doppler shifted. And so it now sees the laser beam coming from the left, or if it weren't moving, it would not. And it doesn't see the laser beam to the right. And therefore, it will absorb light from the left. Now, if the atom were moving to the right, it would see this laser beam tuned to higher frequency, which means this beam would become resonant. And every time the atom absorbs a photon, it slows down a little bit because light carries momentum. And so in this way, I can slow down atoms, and slowing atoms down amounts to cooling. And it turns out that the force I can apply with these laser beams, so that sounds very, you hear, if I shined a laser pointer on your hand, you wouldn't think much. But the force the atoms feel is on the order of 1,000 times the force of gravity, 1,000 Gs. So shine lasers on a collection of rubidium atoms tuned to the red of their resonance, they come to a screeching halt. So they can stop and capture a reasonable fraction of atoms that start out at room temperature in a distance that's about this big, about a centimeter. And now this is routine. We can use laser cooling to cool atoms to about 300 microkelvin. And it's huge forces we're applying to them. But then where quantum really hit home for me was in the next stage of cold atoms. So in 1995, my colleagues at JILA, Eric Cornell and Carl Wyman, along with Wolfgang Ketterle at MIT, achieved Bose-Einstein condensate. It was the first quantum matter, and sometimes called the fifth form of matter. And it was a birth of a new technology in the making. So they said, if you get atoms cold enough and close enough together, they'll turn into a quantum state. And this is a very famous triplet of false color images, but actually snapshots of a cloud of atoms. And here's the temperature, 400 nanoK, 10 to the minus 9 Kelvin. All right, and this is, you see a cloud of atoms, this is their shadow, if you like, and how many atoms. And then as you lower the temperature, you see out of this broad cloud comes a spire, very sharp spire that sticks out, and at 50 nanokelvin, that's about all you see. And this is the first time one could say one was actually taking a picture of a wave function. And this wave function is occupied by a collection of atoms, all sharing the same wave function. So for me, this is the start of quantum 2.0. There are, in fact, many forms of ultracold matter. BEC, Bose-Einstein condensate, is one of them. There are Fermi gases, atoms and optical lattices, quantum computer qubits of atoms or ions are all states of ultracold matter. And just to bring it back to the practical application standpoint, here's that set of clouds in reverse. So we start out with atoms in a quantum state. If you manage to somehow couple this cloud of atoms to microwave radiation, say at 10 gigahertz, all right, about 4 times the frequency of your cell phone, you could take this collection of about 10,000 atoms with 1 photon, has enough energy to melt this entire condensate. So you can make absolutely incredibly sensitive systems using this ultracold matter. So a good fraction of my life has been involved with making ultracold atom technology practical. As I said, my colleagues were Eric and Carl, collaborated with them for many years. While they were interested in the fundamental science, I was interested in applied aspects. So here's Wolfgang Keverly's BEC machine about 1995. This is just all the optics. There's a vacuum system in here. They're not even showing you the electronics, which is in racks off the left here. So that was the BEC machine, his first one. And in 2013, ColdQuanta, my company, came out with the first commercial BEC system. And this is 2 guys who are still at ColdQuanta, but they're also my former students, looking into the whole laser system is in one drawer. And here's the whole BEC machine is at the top, and this is all the electronics. And because we commercialized it, NASA said, oh, that means we can send it to space. And so it's been launched twice. In 2019, this is the second launch of a BEC machine going up towards the International Space Station. I'm very proud of this. This is Eric Cornell and I were at the second launch. This is astronaut Christina Koch installing the second, the upgrade, the second version of the BEC machine on the International Space Station. It's about the size of a dorm room refrigerator. So that was 2019. And it's been making BEC since May 2018 till now in space. So, you can have the physics in place, but to make things easy is hard. So making BEC now is routine, but getting there was hard. And one of the pieces of technology, just to show you one, was atom chips. And this was Science Magazine. It came out in 2017. And they have one of the atom chips that was developed. Actually, the technology was developed by my group at the University of Colorado. And it looks simple enough, but it's very, very special technology made of silicon and glass. You can see through parts and you can not see through other parts. So this is silicon. And then there are glass that you can lay down. So substrates are made of either glass and silicon. And I want to show you something that to me is still absolutely remarkable. So many people, and I think some of you are familiar with the superconducting quantum computers. And here's a picture of IBM's chandelier, all the things that bring wires from the outside world down to superconducting chips that are sitting somewhere around here, or Google's version. And it's brought down to 4 Kelvin using liquid helium, basically. It's brought down to about 10 or 15 millikelvin. By contrast, in our case, only the atoms are cold. The atoms sit in a glass cell, which is approximately 2 centimeters wide, about this wide. And I have one in my briefcase, but right now I won't reach over and get it. And there's an atom chip at the top that seals this cell. So here's a somewhat more artistic version, not as pretty, but easier to say what's going on. here's the glass cell. Here's an atom chip. The atom chip is less than a millimeter. The outside world is about an atmosphere here on Earth anyway. Inside, the pressure is less than a nanotorr, or about a nanotorr. The chip itself is at room temperature. As I say, all of the atoms are cold. And when the thing is working, there's a cloud, a quantum state of matter sitting about 2-3 hairs width away from the surface of the chip. These are at less than a microkelvin. The chip is at 300 Kelvin. So we have a factor of temperature of 10 to the 9 or 10 between this chip and the atoms. And because this chip has a window, we can actually take a photograph of the quantum state. And again, the beautiful thing is only the atoms are cold. Everything else is at whatever temperature is ambient. All right.
Professor Anderson, this is impressive. Thank you so much for the pedagogical introduction. Can I ask you something about the chip? So the atom stays, like you said, a little bit apart from the chip. And so the atom, can you tell us a little bit more of what is it that it does? The atom chip, like it controls all the electromagnetic pulses, I assume, right? But if you could, if it's possible to say something more about that, it's very interesting. Thank you.
Yeah, very quickly. So these are this chip. Each of these pads is the feed through, which goes from the ambient side to the vacuum side of the chip. And we're showing you here the vacuum side of the chip at the moment. And so we send currents, say, through this wire, across here and down to this wire, for example. Actually, this is not the chip that's used on the space station, but so be it. And so we make very strong magnetic field gradients. We don't have to really pulse these chips. Rather, they have almost DC currents through them. We turn them on quite slowly, on the scale of many microseconds, and then leave them on for seconds. So just currents and very strong magnetic field gradients. All right, and that's it. But before then, we've laser cooled them. We magnetically transport them to the chip, grab them using magnetic fields on the chip, and then do something called forced RF evaporation. So on the other side, there's a little coil that's energized with frequencies from about 50 megahertz to a couple of megahertz to carry out forced evaporation. And I'm sorry, I don't really tell you how that works today. I could, but I'm not covering it. How to go from 300 microkelvin to less than a microkelvin. Okay, so these are just wires used to generate magnetic fields.
And what is it that the magnetic fields do then? What's the big thing about them for the atom here? So yeah, I'm a theorist. I really enjoy it. Yeah.
No, so think of the magnetic field serving as a bowl to hold the marbles that are atoms. All right. And so the atoms have a magnetic moment. We can hold them near the chip by applying a magnetic field, and it's a bowl. And the key is that I can cause the atoms to leave the bowl, the energetic ones, by just exposing them to some low frequency RF to carry out this forced evaporation. It's much like how the coffee in your coffee cup gets cold by the hot ones evaporating from the surface. Likewise, the atoms, we remove the hot ones, and then that cools them to the very low temperatures. Okay, for now anyway. Okay, so what are the tools of the trade? You've just learned about cooling. Well, the gorgeous thing about the atoms is we can control them just with fields, magnetic fields, optical fields. And I already told you that when we tune very near to atomic resonance, we can remove energy. But when we're tuned far away, we can still impose forces on the atoms. So when the lasers are tuned far away, these forces are conservative, meaning the atoms don't lose any energy, but we can still trap them. All right. So if we have a beam that's tuned far to the red of atomic resonance, atoms are attracted to the high intensity regions, and we can trap them against, say, the force of gravity, or move them or grab them like tweezers. if you tune them to the blue side of atomic resonance, the atoms are repelled from regions of high intensity, so you can make barriers. And the forces that the atoms experience can be huge. Again, tens to hundreds of Gs to thousands of Gs when we're cooling them. So you don't have to worry about making these things practical to put an instrument on a car or a rocket because the forces of the atom that the atoms see with laser beams are very large. So for example, in the case of the clock, if I have two laser beams that are propagating in opposite directions, they form an interference pattern of bright and dark regions. And if it's tuned to the red side of resonance, I can hold the atoms up against gravity. That's what you saw Junyi did with his clock. And this is called an optical lattice, a 1D lattice. We can also make 2 and 3D lattices and more. And the beauty of this is we can make a perfect array of atoms if we want. All right. And that's utilized for quantum simulation and quantum emulation to do material science studies of condensed matter systems using atoms which are in these lattices. And similarly, you can do quantum computing by arranging atoms in a lattice. Now, in our case, at ColdQuanta, we don't hold them with lattices. Each atom is held by its own laser beam. And so I use the hyperfine levels and laser light, and I can transition an atom by shining light very briefly on it from a 0 state, which is some ground state, to a 1 state, which is a hyperfine level, for example, and back again. Oops, sorry. Let's see if this works. All right, so make it 0 and 1 just by shining laser light. If you should save whether you're here or not, because the camera does disappear once in a while. So, all right, and it can be put in a superposition state just by shining laser beams. And so I can take an array and put them in 0s and 1s and have the atoms interact through something called Rydberg interactions. And I'm not describing them, I'm just giving you an idea that by having an array of atoms, we can make a quantum computer. And we just have simply exquisite control of the atoms. And here's something I find remarkable to this day because it's a simple picture, but the technology it took is rather incredible. If you looked at it, you say, oh, that's nice. But what this technology that is no longer looks complicated can do, for example, is give you a photograph. This is 1,225 cesium atoms. They are 3 microns apart, held in an array of laser beams. So this is actually pictures of 1,200 atoms. That's rather mind-boggling if you think about it. Individual atoms that are controlled, held against gravity, controlled, change state, all by laser beams, no wires. All right. So this whole thing, this whole array, its width is about the width of a human hair. And we control the wave function in principle. We don't do that yet. This is our challenge, to control the wave function that corresponds to these 1,225 atoms using 8 different lasers, controlling beam frequency, intensity, pointing of the laser beams to address the individual atoms to make a wave function. And the laser light provides classical control over the wave function. All right, so this is actually a challenge. This is not a working quantum computer. It just shows that that the qubits don't take up much room, and the challenge is controlling these qubits, which are at very, very low temperatures, about a microkelvin or a couple of microkelvin in this case, all controlled by laser beams.
Sir, one more question. So in this case, in the application of quantum computing, the idea of ColdQuanta is not to move the atoms around, but actually to tune different atoms towards the Rydberg levels where they start talking to each other, right?
Exactly right. Very good. Yes. And this machine is on the cloud, a small one of these, not this many atoms. This is a far future one. A small quantum computer is on the cloud. Fantastic. And you say it perfectly. All right. Great. I'm going to show you an application.
One more question, if it's okay for you.
Sure.
So the lattice on the picture looks almost looks ideal. There are no defects. So how many attempts do you make to make such lattice, and how long can you keep it in this state?
Oh, that's an excellent question. First of all, this is an average. This is several snapshots. But what we really do, not for this lattice, this is just to show that we can trap 1,200 atoms. What we do, though, to say make a lattice of 100 atoms, is we actually have a much larger lattice of maybe 200. And you're right, there's some defects. So we move the atoms from the 200, we move them to fill 100. So maybe there's 60%, 70% loading efficiency, but then we rearrange the atoms so that they maintain a perfect lattice of 100 by 100. Did I answer your question?
Yes.
Okay. Okay, good. So that's the idea. There's always some extra ones or reservoir out on the wings that are moved using optical tweezers into position of the empty sets. All right, so I'm going to show you quite a different application, shaken lattice, inertial sensors, and quantum machine learning to be applied to navigation and guidance, oil and mineral exploration, and earth monitoring. I'm focusing on the technology that it takes to carry out these applications. Just to give you the real life world, when I was a graduate student, at the age of some of you, I worked on laser gyroscopes. Here was the first laser gyroscope back in 1962. And here is a laser gyroscope that closely related to my work. It's about 28 centimeters perimeter. And so that technology is really, really well developed, and is the high bar placed on quantum technology. This is what we have to compete with before anybody is interested, is a gyroscope like this. A gyro is an inertial sensor for rotation. So in atoms, by now, it's a well-developed concept and well-demonstrated technology of taking a beam of atoms and using laser light to split that beam into two beams, and then allowing the atoms to propagate, to reflect with some more laser light, and then recombine them. And then depending on either acceleration or rotation, depending on the details of the system, I measure the flux of atoms out two ports, and measuring their flux out these two ports gives me a measure of the acceleration or rotation with exquisite sensitivity, but it's still very hard to make practical. So I want to tell you something that I think is cool. And when I started doing this, I discovered, as often happens, that the person who really thought of it did it about 15 years before I did. This guy, Pierre Maestro, was actually a postdoc when I was a graduate student. And he had the idea published in 2001, but he's a theorist, so not surprising. It sat around until it could be done. So let me tell you how to train your accelerometer or your gyroscope by trapping atoms in an optical lattice. So this slide is for the theorists in the audience. When you have a periodic potential interfering laser beams, the atom wave functions are described in terms of block functions. And this diagram, don't worry about if it looks strange to you. It won't if you have a condensed matter or solid state physics background. And it's the same thing that describes atoms and lattices. Our goal is to put atoms in a lattice and learn how to make that lattice of atoms into an interferometer for carrying out either acceleration or rotation sensing. In other words, if you think of an atom very crudely as sitting in the lattice somewhere, we wanted to be able to split the atom's wave function. And since the block functions are a complete set, I simply want to understand how splitting atoms to go out in two directions can be described by block functions, and I get the right excitation to say have the atoms propagate in opposite directions, even though they're held in a lattice. All right. So We do this shake by shake. So the atoms in optical lattice are subject to this kind of potential. It's just a cosine wave. And that cosine has a phase. And I'm going to learn how to modulate this phase, that one. So here's a depiction of a lattice, and this is a cloud of atoms. And I'd like to do the same thing as I did in interferometry of splitting the atoms, having them go out and reflecting them. And so through this sequence of split, reflect, here they propagate back and recombine, and then do a measurement to turn atoms that are trapped in a lattice into a sensor. And it's absolutely fascinating because we've used a variety of algorithms, and now so have others, genetic algorithms, quantum control algorithms, to learn how to turn a lattice with atoms into an interferometer and measure rotation or acceleration. All right, so we learned how to shake this lattice in such a way that the atoms do what we want. And it's, again, a fascinating arena. And just to give you, here's an experiment. The shaking function, how you shake the lattice, is not very intuitive. This is what it looks like. So this is the phase as a function of time after we've learned it. And here we show a picture of atoms that have been split from a single cloud into two clouds, and then recombined into a single cloud again. So this is a photograph of the atoms after they've been first split, top picture, and gone out a ways, and then turned around and come back from the bottom picture. And now we have an accelerometer that we've used with atoms trapped in an optical lattice. Why do that? Because atoms in a lattice are held very tightly by that lattice. And so if you're going to have a sensor on a rocket or a helicopter or an airplane, it needs to stand all the shakes and so on of the vehicle, and yet still be a sensor. And that's what a lattice allows you to do. So in fact, we can turn this concept, and there's been some beautiful work by my colleague David Guéry-Edelon in Toulouse, France, that he makes an arbitrary wave function generator, starting with atoms in the lattice, and shakes the lattice in such a way that it can get any wave function. And here's a cute picture. It says BEC printer. Each of these columns is a separate experiment in which he started atoms in the ground state, shook them in such a way that the population, momentum populations, are given by these 7 dots. So these are actually momentum states, and each experiment is a little bit different. And the fact that he's been able to spell out by a series experiment, BEC printer, shows that he has exquisite control over the wave function of atoms in the lattice, just through these learning protocols. In this case, he used quantum control of atoms in the lattice. So here's some of the technology, by the way, to make this practical.
Professor, we have one question. Yeah.
Sure.
Hi, in the BEC printer plot, what happened in the gaps where because there are 7 atoms, where did the other atoms go?
These aren't 7 atoms. I'm sorry, these are the momentum states here on the left. So, so this is from, the units are h bar k, or 2h, h bar k. So these are 0h bar k, 1h bar k, 2h bar k, 3h bar k. So these are little clouds, not atoms, but clouds of atoms.
Okay.
And this shows that, so this is the momentum representation of the wave function of the atoms. Here's some of the technology. This is a complete vacuum system for parts of an inertial sensor. It's about 6 inches long. It's made of silicon and glass. So ColdQuanta has really pushed on this technology. Here it is in a box that's about 30 centimeters by 30 centimeters. And this is on its way. This is part of the components of making an inertial sensor with atoms. I just wanted to show you the technology that ColdQuanta has developed to make these shaking lattice systems and other systems practical. So, you know, the transistor, as you know, was invented about 1946. 1954, you could say that transistors entered the home. Here's a Sony radio. I remember that as a kid. And by now, your smartphone has over 10 billion transistors and is into the kitchen. Lasers, likewise, invented in 1957, 1982. You could buy a Sony CD player, disc player. And of course, by now, you'll find lasers even in your iPhone. No doubt you use it in your kitchen, but I recommend you don't use it in your toaster. So we'd like to see the same for atoms. But the way to think about quantum technology today is it's very primitive. You think, oh, my quantum computer or my clock, it's really cool, it's really fancy, but it's not. It's primitive, and that's the way you need to think about it. And the ideas we have for quantum today are very limited by the tools that we have to explore them. And very few of us, and you're some of the small number, can even think quantum. So we've seen revolutionary ideas emerge from new technologies, the transistor, the laser. It took 20, 30 years before they reached the kitchen. But you have to suppose that today, although it's very hard to predict how, that quantum will eventually be in the kitchen. And so how can you catalyze today what you know is going to make it be in 2040 in the kitchen? And so ColdQuanta, and this is actually a personal passion of mine, is I'd like to enable everybody and their cousin to do quantum technology. And that's why ColdQuanta has made an effort to take first quantum technology and put it on the International Space Station, but now putting it on the cloud. And so this is a bit of advertising, and so forgive me, but as I say, at the same time, it's my personal goal to make quantum much easier than it is today. It's hard to make ultra-cold atoms, a quantum state of matter. So ColdQuanta has put it on the cloud, and now you can log on. It's still a bit primitive today, but watch over time. We'd like to give the community tools for working with quantum matter. And here's an actual machine. This is a product. It's all the controls in a cabinet, and the whole machine is over here on a small table, plus something in this case to control the laser beams to do what we call painted potential, and another system for doing shaken lattice. So by now, getting to nanokelvin is routine. I ran this web interface the other day, and here's 60 nanokelvin. It's just amazing, even to me, even though we did it, that 60 nanokelvin temperatures for quantum state of matter is absolutely routine. And so this machine on the cloud allows you to do this. And ColdQuanta, of course, also wants to make these practical. In fact, we think that eventually quantum technology is going to be in the kitchen. It'll also be in cars. And that means it's small and cheap. So here is an integrated vacuum cell. This is actually the core of an atomic clock. The whole vacuum pump, areas for cooling the atoms, et cetera. And here's one that's packaged a little bit. And here are all the lasers now in a single box. It's about this big by this wide by about this deep. And so eventually we'll have gone from Ketterly to ColdQuanta's machine, a version of it's on the space station, to something that's about the size of a CD player. It's a long way to go, but we're getting there. Long way to go to get in the kitchen, but we're getting there. So in the case of putting quantum matter on the cloud, all the circuitry, if you like, everything is done with light, not for light, but by light. So light confines, it manipulates the atoms, either in computing, where we dress atoms individually, or make a sensor like atoms in a lattice to make a gyroscope. Or in the case of the current Albert that's going in the cloud, something we call painted potential to make atomtronic circuitry. I'm not going into it too much. You have an expert there in Luigi, Dr. Amico, who does atomtronics. But our goal is to make it so everybody else can do atomtronics or shaken lattice or quantum computing by putting everything on the cloud. So this is just showing a laser beam rapidly scanning to define the circuitry that ultracold atoms can propagate. So today quantum is hard, it's hard to understand, it's expensive, it's exotic. But as I said, you should think of today's technology as being truly primitive. In 20 years, less than 20 years, our goal is to make quantum familiar. It'd be every day, it'd be boring. Don't worry, there's still plenty of theory to do, so you'll have a job. But everybody else will have an understanding of what quantum is. In the same way today that gigabyte is a word which everybody understands and uses, though in the 1990s, it was only for the elite nerds. So quantum will be in the kitchen, I think, by 2040, sitting next to the toaster, and I'll hope you'll help us get us there. Some of us have seen as our mission to make that happen, and it doesn't actually matter whether or not it really does change the world. The fact is, you simply have to believe it and work towards it, because that is what will make it happen. Thank you very much.
Thank you so much for such a fantastic talk. This has been very, very pedagogical for many of us, the illustrations, the introduction, and of course, congratulations for the amazing results. I guess we have many questions. I don't know if we should start by any junior. Okay. So, yeah, Philip here. Yeah.
Thanks for the talk. You showed these quantum sensors, like acceleration sensors. How well do they perform? Can you give an estimate compared to other sensors? And how well can they measure acceleration? What is the accuracy?
Yeah, our goal right now, it's pretty primitive technology. Our goal, and we, by we, I mean Murray Holland, myself, and some others at the university, is to make it valid for space navigation with a goal of less than 10⁻11 meters per second squared per root hertz. That's the objective. The key to that is having very long atomic lifetime. And there's some incredibly interesting results coming on the learning algorithms to show that you can use machine learning to make these devices substantially more sensitive by having the goal of having sensitivity. I'm sorry if I didn't take a lot of time to describe that, but you'll see some works coming out of the University of Colorado about the learning. And the goal is to now build these systems to make it that accurate.
I was wondering, when you talk about this learning, this machine learning, this is for how to separate the atoms best, or what do you need it for?
Yes, we use machine learning first to how to make a good interferometer. But it's even more interesting. There's feedback here. I'm sorry. Can you hear me? Can you hear me? Hello?
Yes, we can.
So we use now machine learning algorithms to do the splitting, the propagation, the reflection, and recombine them into an interferometer. We learned that because we can't, it's very, very hard to compute. And it's very hard to know all your experimental parameters. But in fact, now we've shown that machine learning can be used simply to make an excellent sensor, even if not in the classical way of making a sensor. Luigi, this is something that Murray Holland talked about when he was at atomtronics. So later, maybe you can bring others up to speed. But using learning algorithms, you can teach the sensor to be a good sensor for what you're interested in while removing and eliminating sensitivity to signals like vibrations you are not interested in. So the machine learning is very, very powerful for controlling the wave function of atoms to simply make a very good sensor. And while it may be computationally expensive to do that, you only have to learn once, and then you can simply use the sensor. It's been calibrated. It's been taught how to be a good sensor. There'll be much more coming out on this in the future, but I find it incredibly exciting. It is a genuinely good application of machine learning techniques in a quantum systems context. I haven't really answered your question very clearly, but it's just a very practical thing. First, that it's hard to compute, and you don't know your experimental parameters well enough to learn or to shake a lattice simply to become an interferometer without the help of some learning algorithms to tell you how to shake. That's number one. And number two, it turns out you can use learning algorithms to make it a much better sensor than you could if it was simply an interferometer like I drew, but something a little bit more sophisticated. But we'll hope you have another chance to learn more about that.
Hey, Dana, sorry, Cindy.
Hi, Renee.
Thanks a lot for this fantastic talk. And so my question would be, it's like a connection to a discussion which I had once with Philip Boyer.
Yes.
And I asked him in the context of sensing with atoms, so what is the key role of quantum? And then we talked for a long time, and in the end, for me, the conclusion somehow was that it's more about system control, that you're very well able to control specific parts of the system. So for instance, Philip believes that it's very important that for an inertial sensor, that the atom is in free fall somehow. There's nothing which can disturb it. But I didn't really conclude on this. I don't know if you have had some insights on this question of where's the quantum or the essence of the quantum coming into inertial sensors.
Yes, let me say a few things about that. First, I also spoke with Philip, and he agrees that if we're going to make these things practical, that free fall doesn't work very well. And the fact that we use light to control atoms, the clocks, the result of the clocks that shows, despite holding the atoms tight with lattices, we don't destroy their ability to measure time. That's the first thing, that the lattices do no harm. And the second thing is that if you mean by, of course, atoms in the ground state of the lattice is a quantum phenomena. If you mean quantum 2.0, where people talk about entanglement, well, it's still early yet, but you know that when you include atom interactions, it begins to be very quickly almost hopeless to compute what happens. But the learning algorithms still work. And that's what both David Gary Edelon and Murray Holland, who are theorists who have done a lot of computation, have shown about these learning algorithms. Once you include interactions and you get entanglement among atoms, it gets very, very difficult to make any standard theoretical predictions. But for just as one example, if you call squeeze states a quantum 2.0 aspect, David Gary Edelon has shown us this lattice can learn how to put the atoms in a squeeze state. That's an example, and also how to do with atom interactions. So it's early yet, Renee, but I think it's enormous potential of this having a great deal of control over the atoms. Free fall has its problems in a real, in a harsh environment, as a moving vehicle, for example. Lattices ameliorate that, but then it turns out there's also a lot more power to be had with the help of this machine learning to do what computation struggles with. And as I say, you do the machine learning basically once, so you put a lot of time into it, and then you deploy the system and use the calibration that you achieve through learning. I hope this answers your question.
I understand that actually you can make array of cubes.
Yes.
What you need, or what are the challenges to realize gates out of this array?
So
it's true that we have kind of potentially 1,000 qubits or whatever, but do you mean that actually you can work with the thousands already, or
no?
What are the challenges to make a quantum gate?
So right now we have a quantum computer on the cloud that has a very small number of qubits. I think you'll find a publication in Nature that came out in April, I believe. The challenge is controlling, you saw that there are 8 lasers different lasers. And most of those lasers have to individually point to the atom to address them. And they have to have very well-defined frequency, intensity, and pointing. And that's very, very difficult to do. The challenge is not getting the atoms into place. That is fairly easy. To get enough precision over the laser control is the challenge that we face. And that's the challenge we'll face up to about, let's say, 10,000 atoms. And after 10,000, it becomes even much harder still. But it's simply getting the laser beams, the classical control, to be superbly well behaved.
Professor Anderson, it's me, Leandro, again, and this has been a fantastic talk. I want to thank you again for being here with us. I want to apologize for the technical issues that we experienced now, but luckily we could call you on the phone and at least have the chance to ask you a few questions.
Yes.
Questions, and everybody listening to your answers via Luigi's mobile. So let's finish by thanking the speaker again with a big applause. I hope you can hear that clapping hand, and thank you so much for your kindness and your time. Okay,
It's been a pleasure.
Congratulations again for the amazing results. Thanks a lot.
Good luck, all of you.
Touch.
Yeah, bye-bye.
Thank you. Bye bye. Thanks a lot.